Swayam Prabha. Digital India. Educated India.
Welcome. We have discussed the Hodgkin-Huxley equations and briefly explained, at least qualitatively, how the action potential occurs. And in terms of actually observing the phenomena, we need to simulate the system of Hodgkin-Huxley equations in order to fully understand it. So, there will be reading material and codes provided to you regarding the Hodgkin-Huxley equations, which you can use to understand their behavior by using current injections and see what threshold phenomena you can see and so on. There are a number of things that the Hodgkin-Huxley equations actually explained, and in order to actually analyze the system so that we can understand what Hodgkin-Huxley equations can explain, we need to be able to reduce the system to lesser dimensions. So, the system of equations is essentially made up with this vector, let us say x, which is the set of 4 state variables v, m, n and h. Now, the system of differential equation essentially is this is the derivative of x, which is the vector v dot, m dot, n dot, h dot, which is our some function of this vector x. So, in this case what we have is f1 v, m, n and h, f2 v, m, n, h, f3 similarly, f4 similarly, or we can call them fv, fm, fn and fh. So, this is this entire system of equations. It is difficult to visualize and apply a lot of techniques that have been already developed to understand behavior of such systems of equations. And most often what we will see is that if we can reduce it to 2 dimensions by some assumptions, we can understand a lot of phenomena to do with action potentials and in general the Hodgkin-Huxley type equations. So, what we mean by reducing it to 2 dimensions is essentially making certain assumptions, and these assumptions have to be meaningful. Meaningful in the sense that they have to be proper assumptions for a range of parameter values or a region of the phenomena that we are trying to understand, not throughout the entire period of the phenomena, but maybe a part of it. So, the pointers here are if we can see already that m is very fast, very fast, n is intermediate and h is very slow. So, we can assume, like in one case, we can assume that our m is so fast that its dynamics are not required, and m is instantaneously changing to m infinity v. So, we do not need to have the dm dt equations. So, this equation is not required anymore, and m in the Hodgkin-Huxley system of equations can simply be replaced by this m infinity v. So, now we can have h set to a initial value, that is, since h is very slow, we can also remove the dh dt equation and replace h in the Hodgkin-Huxley equations by the h infinity v initial value, or v 0, let us say. That is, the system is starting to be simulated when the voltage is v 0. We can, let us say, assume that h is so slow that h is not changing at all, that is, it is at the original value, it stays at that value from the as it was in the very beginning. So, we got rid of two variables here, one is m and the other is h. So, we are left with essentially a system of two equations, that is v and n. So, now obviously, as we mentioned, these assumptions need to be meaningful. So, that means that the system of equations, this reduced system of equation, has to work in a small range of values or small region of parameter space. So, what we mean is that we cannot explain behavior here that depend strongly on m, that is, the very fast change in kinetics of m, which is we will not be able to explain the threshold phenomena. So, remember that we require the voltage to gradually come up fast and faster and faster till the threshold is reached, and then it goes even faster to produce the action potential. So, if the dynamics of m are removed from this whole set of equations, then we will see that the true threshold nature of of neurons cannot be explained without the m. And similarly, since the time scales at which h starts to change, we won't be able to accurately show the behavior of the system with the v and n kind of system. So, what we have is something that is called the v n reduced system, where m is fixed to m infinity v and h is fixed to h infinity v naught, where v naught is the initial voltage. So, now that we have only dn dt and dv dt to govern the system. So, this will be meaningful in only intermediate time scales, not the very early time for the current injection period, if we are trying to explain the action potential. And obviously, it is also not very useful to explain inactivation behavior, or after the action potential is after the potassium channels have brought the action potential down or the voltage down to complete the action potential, the behavior after that wouldn't be accurate in this case, because the dynamics of H are gone. So, but it will allow us to understand the behavior at the intermediate time scales. Now, we can extend this whole idea going forward, where we can set the n and h to their initial values and have the m dynamics included. That since n and h are both extremely slow compared to m, we can say that we can have a Vm reduced system such that n and h are not changing, they are set to their initial values. This kind of a system will allow us to see the behavior at the very beginning of the action potential, to understand the threshold phenomena, so to speak. And in this case, as you can see, if we have a Vm reduced system, we wouldn't even be able to model the action potential, because potassium currents are gone and H is not there. So, once the voltage increases and M reaches 1, we cannot bring it back down, or rather whatever the potassium channels did, that phenomena is gone. So, we cannot, the voltage will not change since M is 1 and that it will stay there. So, we cannot model the entire action potential, but we can model the very beginning part of the action potential and explain threshold behavior with the Vm reduced system. So, we will go into these kind of analysis when we talk more about the Hodgkin-Huxley equations, but to develop the kind of tools that are required to understand these two-dimensional reduced systems, we will study a set of equations which are called the Moris-Lecar equations. So, this is very similar to Hodgkin-Huxley equations. These were developed to explain the behavior of a particular ganglion cell in a particular species, and they do not have the exact same kind of channels that the Hodgkin-Huxley equations show, but they have similar properties as the Hodgkin-Huxley kind of ion channels. So, what these Moris-Lecar equations tell us is that, or in the behavior of the kind of ganglion cell that we are talking about, we have the same kind of phenomena dV dt equals. So, they have a potassium channel which is M infinity V minus E calcium I external, I need some more space. The C dV dt equals I external minus G calcium. So, we already bring in a term that is new with M infinity V minus E calcium minus G K bar W into V minus E K minus G leak to V minus E leak, and we have dW dt equals the same way W infinity V minus W divided by tau W V, and there is something here called phi, which is a temperature factor, which is not of concern at the moment, just it is a simple constant. So, this is just scaling the dW dt. So, we now need what W infinity V, tau W V, and our M infinity V as a function of voltage in order to describe this whole system. So, what we have here is that these kind of neurons have a calcium channel that can be explained by one activation gate. Their behavior can be explained by one activation gate, which we are describing by this m infinity or m, and it is extremely fast like the sodium channels that we saw, and this is set to m infinity v, as we did in the earlier discussion for the Vn reduced system. They have a potassium channel to explain their behavior also, that is described by the gating variable W, and this is only one activation gate, and the W behaves with the same kind of first order kinetics that we had in the Hodgkin-Huxley equations, which is the second equation here. And V leak, V minus E leak are also as just what we had before. So, here the parameters C, I external of course is in our control, the G calcium, G potassium, G leak, EK, ECA are all obtained experimentally and is provided if someone simulates this system of equations. And we have a few other parameters that describe the W infinity V and tau W V and M infinity V. So, what we have for the M infinity V is half of 1 plus tan hyperbolic V minus V1 by V2. So, this is another parameter, this V2 is another parameter added to the list. So, those are again experimentally and empirically determined, and this is the best functional form that the Moris-Lecar, I mean the people who developed the model, they came up with. This is explaining the data the best, and V1, V2 are obtained from that data set. Similarly, W infinity V also has the same form, which is half 1 plus tan hyperbolic V minus now V3 by V4. So, V3 and V4 essentially describe are the new parameters that describe the W infinity V, and essentially as you can imagine, if you were to plot this, remember they are going to be like the activation plots that we had for M infinity V and N infinity V. That is, they would look very much close to a sigmoid. They are obviously not a sigmoid. This is the functional form that is best explains those plots for these particular neurons. And now tau WV is again best explained by twice cosine hyperbolic V minus V3, the same V3 over there by V4. So, if we are provided with this V3, V4, V1, V2, then we have how the tau W changes with V, how W and M change with M infinity change with V. So, with all the other experimentally determined parameters and these functions, we have whatever is needed to be able to simulate these equations or numerically solve these equations, which is that the first equation with the dV dt and the second with the dW dt. So, this system of equations is what is our Moris-Lecar equations, and this set of equations will tell us a lot about how the action potential behavior and a few other things. So, if we now think of solving a set of differential equations like this numerically, let us say this is the C dV dt equals I external minus the I calcium minus I potassium minus I leak. We can replace those terms by the G calcium bar with the gating variables, and we have the dW dt here as W infinity V minus W by tau W V. So, to solve these equations, as for any system of differential equations, we obviously need a starting point or initial condition. So, if we are trying to simulate this equation, often the starting point can be the resting state or the V rest, which can be determined from these set of equations numerically, and that would be the value at which the total current is 0. When there is no current injection, the total current is 0, and there will be some V rest. Now, the solution to this set of differential equations would be of something that shows how V is changing as a function of time. If we start at V rest and W starts at W infinity V rest. Remember, what we mean is that we are at V rest for a long period of time, which means W's initial value is W infinity V rest, that is the steady state value, and obviously the initial value of V is V rest. So, from V rest, how the system is evolving over time is what is V t, and it is the solution that we are seeking for some kind of phenomena. I mean, we can have a perturbation of the system to move it from V rest with a current injection or a voltage clamp, what have you. We can solve these equations and try to understand what is happening, and parallelly we also will get how W changes with time. So, these are what we are seeking for different initial conditions of V rest and W infinity. So, if we now think of the V and W going forward as a pair of state variables, we can always plot them on a plane with V, let us say, on one axis and W on the other axis. What we have here, let us say, is V on this axis and W on this axis. And the initial condition, let us say that V O and W, let us say, is some particular W 1 and V O. If we start the system at this particular point, the solution to these equations is simply going to be a curve in this plane. What have you? That is, this curve shows how V and W are changing together over time. So, time here is along this curve. So, at the next instant it is here, the instant following it is here, and so on. So, gradually the system is moving. That means, we are showing how V and W is changing with time. So, this is our solution. What we do, what we call this plane is the phase plane, where V and W are the state variables. So, if we want to understand the behavior of V and W in this, we must note that at any point in this plane, let us go, V is here and W is here. If we consider this particular point, let us say, what we have from the system of equations is the value of dV dt and dW dt evaluated at this point. Let us call this some V P and WP, let us say. So, this is evaluated at VP WP, this is evaluated at VP WP, this particular point. Which means, so remember, if we go back to the previous slide, given all these variables and parameters, we can calculate what dV dt is going to be and what dW dt is going to be at that particular point VP WP in this plane. And what does dV dt and dW dt tell us? It tells us how V is going to change with t at that location. Similarly, dW dt is going to tell us how W is going to change at that location, which means if we think of dV dt as a direction and dW dt, that means that if we think of dV dt as the movement of the system along this V axis and dW dt is how the system is going to move along the W axis, then the two together gives us the net direction of flow. If this is the size of dW dt, this is the size of dV dt, and if it is positive, then on the positive direction in these two directions. So, the net effect is that the system will try to move in this direction if it were here. So, if we can consider very small time windows from this point, and we can, since we can calculate dW dt and dV dt and dW dt, we can find out exactly where it is going to be in the next small time instant later. That is, we can show, or rather we can calculate the position of the system in this V and W plane, that is the new value of V and the new value of W at a very short time interval later. And at that location, let us say that is Vp plus some small delta and Wp plus some small delta W, we have a new dV dt and a new dW dt, and there we will have a new arrow that will direct the system in that particular direction. And now you can imagine that with these small steps, we can essentially show how the system is going to behave in this plane if we start the system at a particular point. Very qualitatively, if we create a grid of points here, a fine grid of points in this entire plane over the range of values of V and W, then for each point in the grid, we have a dV dt and dW dt, and we can plot tiny arrows, which is what we call a quiver plot, that tells us how the system is going to move at each and every part of this space. And if we can somehow plot these arrows, we can actually predict how the system is going to behave quite well, in the sense that we can say whether it is going to go to this direction, or ultimately going to go to a particular point or not, and so on. which we will see. Of course, ideally it is best to be able to numerically simulate the system as we were discussing with those small time steps. The problem is that those small time steps has to be determined in the sense that how small is good enough. And for that we have solvers that help us simulate these systems as fast as possible, so that we do not have to simulate them at extremely small time steps, which is going to be very time taking. So, those ideas will be there in the codes that will be provided to you for simulating this system and understanding the behavior of the Moris-Lecar equations. So, we will continue from here to with the Moris-Lecar equations to understand lot more things about these Hodgkin-Huxley set of equation or this type of equations and how to understand their behavior. Thank you.